that very much. It's always difficult to follow up after Anders, but I mean, it's a great speaker and an inspiration to all of us. Thank you very much, Anders, if you're still there. All right, so today I wanted to speak about one line that we have been following in stochastic optimization, trying to produce some adaptive variance reduction and extend that work into Quasi-Newton methods in the presence of stochastic samples. Yes? Second try. Hello? Is it better now? Sorry. So, all right, so I was making a small introduction to the work today, which is a collaboration with André Carlon, who is there actually, is a postdoc here, and in a couple of months he's transitioned to Germany, and Luis Espas, who used to be a member of the group in Chaos and then in Aachen, and now is a faculty in Nottingham. All right, so I will not keep dangling here. Our problem is a classical stochastic optimization problem where you want to find an optimal design, essentially, of value for control psi, right? And you want to minimize the expected value of a function f that depends on psi, essentially, and theta, which is a random parameter. You do not have the possibility to compute this expectation exactly, or is rather very costly, for example, and you would like to optimize, therefore, with respect to psi in an efficient way. There will be assumptions on the function f, on regularity, and some sort of convexity throughout the talk. And applications, I don't need to go too much, right? I mean, they're everywhere. It's stochastic optimal control, computational finance, optimal design, machine learning, etc. So this talk is full with these things. The important thing is that I will assume that I have the ability to sample directly theta without having to do any tricks out of a distribution pi, right? And I will have access also to the evaluation of f without any little f, without any errors. So there is no discretization in this talk, only optimization, if you wish. Of course, in the context of machine learning, for example, that expectation that I was talking about will be just a finite sum. The point is that this number n capital may be very large, and therefore I like to explore other possibilities where you don't have to compute the whole sum every time you have to take decisions on how to move the parameter xi towards the optimum. What I'm going to talk about is covered in one preprint on multi-iteration stochastic optimizers and a recently published paper on Quasi-Newton methods using, again, the things that I'm going to explain on the second part of the talk. All right, so let's recall a little bit of the brief of the theory. We produce, I mean, in this context, we have iterative algorithms, and they're based, for example, on a line search, where this VK is I mean, in principle, a noisy evaluation or approximation for the true gradient, right? I mean, when I talk about true gradient, let's see if I have the pointer. No, I don't have a pointer. The top. Okay, so I will not turn it off if I press it. Okay, thank you. I was talking about essentially this line here, and the VK here is going to be some kind of estimator for the desired expected value of the gradient of the little f, right? I mean, sometimes we talk about, I mean, I think throughout the talk, I'm going to use f capital as the notation for the expected value of little f. Therefore, this here, just assuming the standard commutativity, is going to be the gradient of f capital, right? So that's exactly what it is. So this VK here will be some kind of statistical estimator for this quantity, right? And it's going to be just approximator. And there are many methods that different iterations of the optimization process can I make. In this case, this is the Robbins-Monroe algorithm, stochastic theta. direction line search, right? And we choose some kind of eta k here, which is a learning rate that has certain properties in terms of variance to zero and summability of the squares. This, for example, is one of the sequences that one could use to ensure convergence towards the optimum. Okay, so it's important here the and this particular case, not even like to zero. One would like to use information from the obtained steps in the optimization to produce another estimator, right? That in some sense can control this relative error. So it's a relative error. Here you see the difference in L2 between the estimator and the actual gradient we would like to compute, right? For a given value of psi k, of course, along iterations, and this should be bounded by some factor that is less than 1, called this epsilon, times the norm of the desired quantity squared. Okay, so it's a relative error control. If you have that, then you can get convergence. Of course, the question is at what price, right? So assuming some Lipschitzianity on the gradient here with some constant L capital here and the control that I just mentioned, you can actually show some kind of decrease in the optimal value of the function that you would like to evaluate, right? And here epsilon is coming. Here you see that this is going to be a positive value, less than 1, and then L capital, of course, will make it smaller. But you still have some decay. This, in fact, if you add some kind of convexity here, for example, this is a weaker version of convergence with this mu parameter, you get now some kind of exponential convergence with respect to the number of iterations, right? But yet this is not telling exactly what is the cost that is incurred in terms of gradients, right? Gradient evaluations, because I mean, as you get closer, as I said, keeping this epsilon constraint in the relative error will become more costly. So first thing you see here, there's the effect of the epsilon, right? And the effect of this condition number, which is a L capital divided by mu in this context, right? So this may be a large number in practice, so that will make the convergence here painfully slow sometimes for large condition numbers. All right, but still you get this factor k, right, in the exponent, and that guarantees the convergence. Still, we're making strong assumptions on this function, right? For example, the assumption 2 and the Lipschitzianity. All right, so what about the SGD with fixed step size? Well, if you want to control the relative error in this SGD, right, to guarantee that kind of convergence, we recall the true gradient norm is not known, right? So you try to estimate it as well, and it may not be simple to estimate this true gradient norm precisely when you get closer to the convergence, that is when the gradient of the mean gradient is actually becoming zero. So you're trying to estimate something that is sort of a rare event. So this is difficult in principle as you get closer to your goal. The second thing is these covariance of the gradient samples have to be estimated on the fly. That's not so difficult. But the third point is that the gradient variance actually, or covariance to be more explicit, causes the iteration cost in terms of a gradient evaluation samples to grow fast, right? So we have to do something about it. So that's why we do this variance reduction. So what is MICE? MICE is just an estimator that uses control variates along iterations, right? This is an idea that has been produced in other methods. We just try to do it adaptively. So adaptively, we keep as an index, we'll call this hierarchy, iterations. So if you start from iteration 1, for example, and you are in iteration 20, for example, this set may have just 5 indices, choosing to maximize the profit out of this estimator. So yes, this estimator will be coupled with an error control on the relative L2 error connected to this epsilon that I was talking about. And the result will be combined or can be combined with any first order stochastic optimization methods like SGD, Adam, and so forth. Okay, so it's rather flexible and you can use it in many occasions. The good news is that later we will be able to couple this also with a Quasi-Newton type of method as well. Okay, so how does it look? Well, is maybe a little bit painful, but let me go through it just to show you that it's not that bad. So suppose that you start in a certain iteration, the optimization procedure, right? And we start producing iterations, say xi0, xi1, xi2, and so forth. That is the index k. And up to iteration k, we have all possible iterates, right, from 0 to k. And we're going to choose a subset of those iterations, right, that we call Lk. And this subset of indices will be the ones that we use for our estimator. So how does this estimator look like? Essentially, it will be a telescopic representation of the gradient that we would want to estimate, right? The telescopic summation will be done across the indices that belongs to this Lk. And for each of these indices, essentially, we will average differences of sample gradients. Okay, and the difference of the sample gradients is written here. You see that we are evaluating at psi here, psi L. L is one of the indices here in this Lk, and the previous one in this family Lk is called Pk of L. This is a previous of K of L in the family Lk of indices. Okay, so this is just a difference of gradients. It's the kind of difference of gradients that you will see in other estimators. It's just that here this index set is changing, right? So we need this notation to keep track of the different indices that matter here. If you don't drop anything and you keep everything in this history of iterates, well, this formula 11 becomes this essentially, and this is a bit more explicit, although not practical, but just for the sake of showing how it looks, I write it here. So you see, you sum over all iterates, and for each of the iterates, you average difference of gradients between the index, right, psi and evaluation here at psi L, and the index L minus 1 evaluated at psi L minus 1. And most importantly, here we are using the same theta alpha for coupling the two gradients, right? Otherwise, you don't get any benefit in this method, as it happens with multi-level Monte Carlo or any worth of using the hierarchical method in sampling, right? So this is very important. And then in the base point, you just sample the gradient itself, no average whatsoever, right? And now you have to pick in a wise way the number of samples here that corresponds to each of the terms, right? M0k and MLK here to minimize the work to achieve still this constraint on the control of the relative error. Of course, we don't do this. Actually, we do this, and we drop many of these indices in between 1 and k. And please do not, even though this may look deceivingly simple to a multi-level type of approximation, remember there is no discretization here. So the xi's are just points in a sequence, right? So there's no discretization in this thing. There's no levels for that matter, and there is no independence in the sum, right? Because I mean, the xi1 depends on the xi0, so the independence, or the dependency structure has to be disentangled very carefully here to keep track of this sequence. Okay. Okay, so how does it look pictorially? You just have the first point, right? You sample M00, gradient samples evaluations. You take the average of those, for example, and then you take with that a step towards Xi1. When you're in Xi1, now you're going to sample differences between the gradient samples at point Xi1 and the point Xi0 using the same theta alpha. Those are M11 samples, and then you add a little bit more of samples to the original base point just again using some optimization formulas. And then with those two, you construct the gradient, the mean gradient estimator at this point, and then you take a step towards Sag 2 and so forth, right? So I'm not going to worry you keeping like this. But what is important, as I said, is that for practical purposes, this is crucial actually. LK should not contain all the indices from 1 to k. In fact, selectively, every time you add a new iterate information, right, from psi k, you may decide, for example, to drop the previous psi k minus 1 for efficiency purposes, keep some part of this LK, or even say, okay, this is not worth keeping. I restart everything, and my current psi k becomes my base point, and I restart the algorithm. This, in practice, they and we will see some numerical examples showing you this. These operators actually play a huge role in improving the performance of the coupling of mice with different stochastic algorithms. The one that at least when you consider the effect of the condition number, the one that plays the highest role is actually the restart. But the other two help as well. They reduce not only the time for computing, but also the memory, right? Because I mean, the longer the set of indices that you have to keep, the more information about gradients you have to keep as well. Okay, so these are just dropping and clipping and stuff, so I'm not going to go through that much. You can ask me, but essentially they do what I'm telling you essentially, and if you want, we can discuss the different decisions that one has to take in terms of optimality to decide when to use each of them. Okay, so one can show in terms of gradient sample cost, or for example, the coupling of this mice estimator with the stochastic gradient descent using this epsilon control. Well, in that case, you have some extra assumption on the strong approximation of the gradients, right, for nearby points and the same theta, right? That's an L2 approximation that has to hold, and that connects to this constant sigma that is here. But in that case, if you try to stop the algorithm with essentially this criterion, it has to essentially have the gradient of the true f xi k less than tall with this inequality. Well, then the expected value of the cost in terms of gradient evaluations will essentially be connected to the tall. This is the same tall. It's not in red, but it's the same tall here. The epsilon that you had in this inequality, and some other constants that relate, for instance, to this L2 approximation of consecutive, nearby points gradients, and the kappa that connects to the condition number of the problem, right? That was a L capital that was connected to the Lipschitz constant in the gradient, and the mu that was this Polyak estimate, right? And there's a lower order term here that is not worth much commenting on. You can still optimize this with respect to epsilon, and then get one value that essentially is O1. If it doesn't matter if you do it exactly, this value is rather robust. This method as well. Of course, you shouldn't get too close to 1, right? Then you spoil things. All right, so you can have some results, as I said. But what about practical computations, right? How does it work? Well, first of all, let's consider some examples that are strongly convex, and those classically are logistic regression type of problems, right? Where you have your data, xi, and the noisy evaluations, yi, and you try to reconstruct something that matches essentially the yi's for different evaluations of the xi's, right? And there are some penalization here as well, because this may not this formulation alone will not identically define the xi's, right? So you need to penalize a little bit, like it was done in the previous talk, the norm of psi to get a mu that is not exactly 0, just to put it in the light of the previous assumptions. In fact, lambda here will be essentially mu. So lambda will be controlling the conversions through the condition number, right? So as lambda goes to 0, the condition number kappa will blow up, and this will delay everything. So in practice, one has to treat lambda as a hyperparameter, right, and choose it carefully as well. So let's see some examples with different sizes of data, right? I mean, one is with 8,000 data points, and the other is essentially with 60,000 data points. The number of decision parameters here is of the order of 100. This is the order of 10. The condition number is essentially 10,000, right? In one case, and in the other, essentially, is 6 times 10 to the 9. Really pretty nasty, right? So this is going to be tested thoroughly now. So what do we see? Well, we compare different methods for the logistic regression, right, that I just said, and we run the algorithm essentially with independent seeds 100 times to be able to create some confidence bands, because I mean some of a single realization may not be telling you exactly what happens with the distribution of the runs of the algorithm. So here you see different comparisons, right? SGD coupled with mice is the one in blue here, and you see that it has some variability, right? But still behaves very well in terms of the cost. Here, the cost is a number of gradient evaluations, as I said before. Of course, I could show you just the iteration, right? But that would be completely unfair. You really care about the actual cost in terms of how many gradient evaluations you have to show. But even if you do the cost here, you see some advantage with the other classical type of methods, right? And here's the thing that I was telling you about the operators, right? What we have here is a quadratic cooked up problem, right? But it behaves pretty much in the neighborhood of the optimum in the same way for many different problems. So this is not just a fluke, right? It's just something that you can reproduce quickly to see that what we say is actually true. So here you compare two things. One is a mice that is actually in the proof that I showed you before. Is SGD mice without any of the dropping, restarting, and clipping. And you see that to get to the optimum, right, up to a certain tolerance, you see that the sampling cost is scaling with respect to the equation between L and mu, right? What we call the condition number, quadratically, right? And if you look at the proof, that's exactly what was predicted. There's a square here, right? And there was a kappa here. So you expect things to get, for a fixed toll, quadratic with respect to k or kappa. But if you add the operators, the restart, the clipping, and things like that, this cost not only drops dramatically the constant here, you see that you're changing essentially from 10 to the 5 to a bit less than 10 to the 3, but the dependence on the kappa becomes linear, not quadratic. This is outside of the current theory. So I think it's worth exploring for sure. As I said before, if you look at the effect of the different operators, the drop, the clip, the one that really makes a huge difference is the restart. Okay, so maybe a way to address the theory, we have not done that yet, would be just to start considering the restart and not the others to try to explain this very useful feature of the mice with the different operators. Okay, so suppose that you go to the other case where you have a very, when you have this other case, right? Let's see. I think I went through this already. Oh, come on. I should go the other way. Yeah, so here's the second part of the talk. And essentially I'm 10:30, so that's not that bad. As we saw before, there's a bad influence on the kappa, right? The condition number of the Hessian, essentially, on the behavior of first order methods. That's natural, it happens. I mean, it has the counterpart in linear algebra solvers, right? All of them essentially suffer from the large kappa numbers. And what do? Essentially, we precondition. That's a way to deal with it. But for that, you need good information to precondition. If you do it in the wrong way, you can make it worse. So that's that's what we have to do here, to do it carefully. And what's the challenge, actually? If you talk about stochastic optimization and the difference between that and deterministic optimization, in deterministic optimization, this is a well-known fact, right? You have all the Quasi-Newton methods that build based on difference of gradient evaluations, mimics of the inverse of the Hessian or the Hessian itself, right? And you have VFGS and many others, right? And even memory limited versions of those as well. Very efficient. They deal with the problems very well, and that's it. So what's the difference here? Well, if you want to actually get into this game again and say, okay, instead of just having VK that was a noisy evaluation or approximation of the mean gradient, here I want to put some kind of approximation of the inverse of the Hessian, right? My only information that I will have, right, is essentially samples of the gradients. So let me put this in context. In Quasi-Newton methods for the deterministic optimization, we have access to these differences, right? Remember, F capital was the expected value that I wanted to minimize. So F capital here will be taking the gradient, and then this will be the gradient at the previous point, and the YKs are essentially the input, and the SK, of course, difference of the points, are the inputs, these pairs are the inputs for the construction of all these Hessian approximations based on BFGS, limited memory, BFGS, and all the other versions, right? I could go forever in that. This is a well-established area. Things are working fantastically. What's the difference between this case and what we have? Well, in what we have, we don't have access to this. Remember, we cannot compute expectations exactly. Instead, we have this, right? These are differences between samples of gradients, all right? This is what we have. So big thing, because here there is no error in the evaluation of the gradient. Here, potentially, one error. In practice, though, because of the construction, right? I was telling you about mice. Well, the natural thing to do in mice and similar algorithms is that actually you take batches, right? So you take differences of gradients, and then you average across different samples, IID samples of these theta's that were the origin of all this randomness here. So you have these sort of empirical averages of gradient differences as your input. Instead of having the exact difference, you have this Y bar. Of course, what do we know? As an approximation of YK, Y bar K will be an unbiased estimator, right? And not only that, as M gets larger, it will start concentrating around it, right? And of course, when it concentrates, the best approximation that you can have, right, as a distribution essentially is a multivariate Gaussian, right? So if you want to kind of rethink this problem and say, fine, I admit the fact that I'm a criminal, right, and I'm not computing this expectation exactly, I have this noisy evaluation instead. Well, this becomes essentially a statistical problem, because I'm trying to find a parameter, which essentially is either the Hessian or its inverse, and I have data which has a determined model, right, of distribution that gives a good approximation, in this case, the multivariate Gaussian, right, given the parameter, okay? So now, what I was saying is that the difference between this Y bar K, that was the samples, right, minus B here times SK, where B will be the approximation of the Hessian, if you wish. B itself, the matrix B, is the parameter. This will be a likelihood distributed like, say, a normal with the covariance of the gradients here divided by M, the number of samples that I use for that matter. Okay, so it's good to have a likelihood now with respect to the B. And now that we have a likelihood, we could say, fine, if we are seeking either B or its inverse, we have a likelihood here, and we could pose everything as a Bayesian estimate in the space of matrices. Now, any matrix? No, not really. We know a lot about the Hessian and its inverse, right? In fact, we know they are symmetric, right? They're positive definite. And not only that, in particular problems like the logistic regression, like I was describing before, we have bounds on the spectrum. We know a lower bound on the minimum eigenvalue, and bound also on the maximum one. So we could enforce them as well. So we have prior information that we could encode in a prior distribution in the space of matrices and a likelihood. This is an excellent setup for a Bayesian type of estimate. Now, what could happen here? Well, if things go wrong, you could have like a nasty looking posterior distribution in the space of matrices. That wouldn't be cool, right? Because you are trying to do this as a tiny sub problem inside of an iteration for an optimization. You definitely do not want that, okay? So what is it going to happen here? Let's see. I'm going to write just a log posterior, right? So what you have here essentially is the negative log likelihood. Of course, this was a Gaussian, right? So what you see here is the precision matrix associated to the difference of the gradients, right? So you have the sum across the different iterations, right? That we keep in this mice. This is again the B is the parameter in this game. SL and the Y by L are the data, and that's again the negative log likelihood. What about the negative log prior, which will be the other part that you need, for example, to set up a map type of estimation? Well, to stabilize, right? You want to take a proximality term with respect to the previous estimate of the Hessian, right? So in the previous iteration of the optimization, you got B hat k minus 1 as your optimum. Okay, now you penalize the difference between B and B hat k minus 1 in some norm. Here we chose the Frobenius norm with some kind of weight that we choose here, right? Square. So this is a convex term, and rho is positive. This term is here very intuitively in terms of approximality formulation, but also is the one that guarantees the strong convexity of this log posterior. Okay, the other two terms are convex, no problem, but they may not be strongly convex. So they may not be enough together with the third one to determine a unique B. So we need the first. So here beta again is a positive parameter, and here you have the log of the determinant of B minus mu hat times identity, where mu hat is the lower bound that you want to impose on the spectrum of the B. And similarly, you have a term here with L hat, where L hat is the one that you want to enforce. You could play with mu hat and L hat, not just as hard bounds provided a priori, but you can use the hard bounds and use you move across iterates mu hat and L hat also to accelerate the convergence. These kind of log penalty, log barriers, right, are very common in optimization, right? And interior point methods are classical for this kind of penalization. And this indicates that following that theory, right, if you want to deal with this kind of optimization, you should at least take into account the path following type of updates for the beta, just not to make the log barriers too stiff, right, and the problem too difficult. Just as a warning, right? I mean, but okay, now we have a strongly convex function. There's a unique optimum for this, and we can optimize it with respect to B. Do we need to actually optimize it to full accuracy? Definitely not, right? We just need a decent enough estimate for B or its inverse, right, to get a reasonable line search after preconditioning. So this is not going to be solved to full accuracy on each iteration. That's the first thing. The second thing is that, okay, how we made our life more difficult, right? We started with the optimization of a vector that was called Xi, right? And that was a stochastic problem, right, for optimization. We didn't know the information about the Hessian of that problem, and we had to kind of come up with at least this formulation to provide this estimate for the Hessian. Now, again, we started with optimization that was stochastic with vectors, and then suddenly we have an optimization on matrices. A much more complicated space. In principle, things could explode in terms of cost, right? It's scary, at least, right? The first time you see it. But there's a good thing about this problem, right? It's deterministic. it is not so difficult to compute in terms of gradient evaluations and even Hessian evaluations. If you do the computations here, you can see that you can compute the gradient in an effective way, just using matrices, not higher order tensors, as you would guess from the first time you see this. And even the action of a certain perturbation along the Hessian on this problem can be computed in terms of matrices as well. No need to go into tensors, extremely effective, right? Extremely effective. And indeed, because of the fact that actually the problem is strongly convex, you can actually use an effective method like a conjugate, Newton conjugate gradient, right? With a backtracking and measure line search. And essentially this works very, very, very well. Okay, so no problem. You just use the proximality regularization and the path following strategy to deal with this optimization well. Okay, so if this works fine, right? The resulting Hessian approximation, or essentially the inverse that you're going to use, hopefully is accurate enough, so we see a better behavior of the stochastic optimizers once we precondition with this obtained approximations of Hessians or their inverses. So let's see one logistic regression with the so-called mushroom set. Again, this was an optimization of essentially 100 parameters with essentially 8,000 data points and a condition number of 12,000. Okay, it's large, but not super dramatically large. Okay, you expect some difficulty if you use first order without any Quasi-Newton. If you see SGD here, okay, that's some good job, right? If you do SGD mice, right, with the variance reduction, well, you get some improvement, right? But okay, is a continuous orange line. If you actually couple this SGD now with the Bayesian estimate of the Hessian, you start seeing something that changes and improves a little bit more, definitely, right? And it's just not with SGD mice, right? I mean, if, for example, you couple this with SARA, right? You will see that SARA improves as well, right? And even when you do SVRG, you will get a similar advantage as well, right? So you can couple this with different methods. It's very flexible, and of course you could ask, for example, how do we choose the number of iterations that we use to update the information of the Hessian? Well, this we don't have a full theory yet, right? It's work in progress, right? But we want to show already the potential without much tuning of these tools, right? They really work and they produce stable advantages. If you now go to the case where kappa is essentially 6 times 10 to the 9, right? That's a hard cookie. If you try SGD or SGD mice or any version of these first order algorithms, they just break their teeth against the wall, right? I mean, really, it's really, really nasty. But if you actually combine, for example, SARA with this Bayesian estimate, at least it will stagnate in a better place. And in the SVRG, the same somehow. But if you actually combine now the variance reduction of the mice with the variance reduction essentially for the estimate of the Hessian and its inverse, you get something that even, yeah, seems to be doing better here. And we tested extensively, and this is not a fluke. Okay, yeah, I think that is a sufficiently large kappa to make you excited about this game. Okay, so that's essentially it's a little bit of the references that were related to the talk, and I thank you very much for your attention. I think I am within the bounds of the talk. So, thank you very much.